Okay, so in this video, we're going to shift our thinking from being just simply resistors in series. So we're going to break this down into two parts. The first part is we're going to look at capacitors in series and parallel. And then in the next video, we're going to combine the two types of circuits we spoke about, a resistor circuit and a capacitor circuit, and we're going to put it all together into an RC circuit, which have many real-world applications. Okay, but first, let's talk about some of the little things about capacitors in series and parallel. So remember, capacitors are where we store charge. Okay, so if you're looking at like a motherboard or any kind of circuit board, these are the ones that are little blue. They're usually wrapped in like a blue plastic. Okay, because that plastic is your insulator. You don't want that charge coming out on its own, and so they wrap it in a blue plastic. It's what stores the charge for later to be discharged and to actually use. Right, and a lot of times they're used in timing type situations. Okay, so capacitors are connected together in parallel when both of its terminals are connected to each terminal of another capacitor, right? So the voltage connected across all the capacitors that are connected in parallel is simply the same. So they're going to have a common voltage. So the common voltage would be the voltage across capacitor 1, or sorry, it should be the total voltage, not the common, but so the voltage of the system. It's going to be the voltage across capacitor 1, across the voltage of capacitor 2, across the voltage of capacitor 3. Okay, dot, 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 right? Because you can have an infinite number of capacitors in your circuit. So when capacitors are connected together in parallel, the equivalent capacitance right in the circuit is equal to the sum of all the individual capacitors added together. So the total or equivalent capacitance is simply C1 plus C2 plus C3 plus dot, dot, dot. So one thing to note, it's the opposite of resistor circuits, right? Where parallel, we did that whole 1 over bit, and it comes from, right? We're not looking at potential difference, we're looking at the charge, right? And so what happens is if I find the charge across the charge total, right? I know it's going to be the charge across 1 plus the charge across 2, right? And I'll just do 2. So Q total is going to be C1V1 plus C2V2. But we know that the voltages are going to be the same. And so you end up with Q total equal to V total times C1 plus C2 plus dot, 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 right? And so this right here is your equivalent capacitance, okay? Now, when capacitors are connected in series, right, they're what we call daisy chained together, right? So daisy chain means connected, right? It's like they're immediately holding hands, right? So that would be capacitors in series. Capacitors in parallel, again, the current flowing through your system would have a path, okay? So for series connect capacitors, the charging current flowing through the capacitors is the same, right? Which means your I total would just be I1 equals I2 equals I3, dot, dot, dot. Right, capacitors connected together in series must have the same charge. So Q total is Q1 equals Q2 equals dot, dot, dot. Right? Now, but when determining the equivalent capacitance, it's going to be R1 over okay. Again, it does come from this Q equals CV equation. Right? And so you would solve this for voltage, you get Q over C. but if the charge is all the same, right, the voltage, this is going to be simply Q times 1 over C1 plus 1 over C2, and there's your equivalent capacitance. All right, and so let's look at a couple of examples. Well, one example of breaking it down, and another one just a ranking task. Okay, so find the charge on the potential difference across each of the following three capacitors in the figure. Okay, so just like we did with circuits, we need to break it down to find an equivalent capacitance, a total equivalent capacitance, so that we can figure out how much voltage, how much charge, and so forth is going through each part. Okay, and again, we can follow those rules for the circuits that we talked about. All right, and so we know that we're going to have a current flowing through. Okay, we know there's going to be a current. The current for the C1 there, for the 3 microfarad, is going to be whatever comes out of the battery, and then that's going to get split, right, to go down the path, okay, and then meet back up, all right? And so let's start breaking this down. So the first thing we need to do is find the voltage really across the 3 microfarad capacitor, okay? And so let me get a little bit of bearing on my note because I just kind of wrote things down quickly. So what we need to do is first thing we do is find the total charge, right? And so we're going to find Q total is C equivalent times the voltage, but we need to figure out what is the equivalent C, right? Sorry. So to find the equivalent C is I need to do a little bit of stuff over on my diagram. So I know that the parallel capacitors are going to have a 6 microfarad equivalence, and then I'm going to have a 1 over 3 plus 1 over 6, right? Really, it's 3 times 10 to the negative 6, 6 times 10 to the negative 6, right? And it's going to be my 1 over C EQ. And so I'm going to do 3E negative 6, 1 over that, plus 6E negative 6, 1 over that. I get 500,000, but I got to go 1 divided by that. And so my equivalent capacitance is going to be 2 times 10 to the negative 6 coulombs, okay? Not coulombs, farads. Coulombs is the charge. Those are going to be F, not C, okay, or 2 microfarads. And so now I'm going to come over here and find the total charge. So it's going to be 2 times 10 to the negative 6 farads times 12 volts. And I'm going to get a charge, going to be 2.4 times 10 to the negative 5th, all right, and that's going to be coulombs. So now I can go to C1, right? I'm going to find the charge and potential difference across that. And so I know that from my rules above that the charge going through C1 is going to be the charge coming out of the battery. Okay, that's this, oh, sorry. That's this rule right here. So the voltage, so we know what the charge is. The charge across Q1, or Q1 will be the 2.4 times 10 to the negative 5th coulombs, right? In fact, just like we did with the circuits, we can make a little chart, right? But instead of it being, you know, VIR, we're going to do, let's see, 3 microfarads, 5 microfarads, 1 microfarad, right? And so I've got Q, C, V, and then I can have total down here. I don't need the, actually I don't need the C because I already have, the first column is the C, right? And so to find the Q for the 3 microfarads, that's just going to be the Q coming out of the battery. It's going to be 2 times 10 to the negative 5th coulombs. Now I can do my V equals Q over C, right? And then the other one will be you got Q equals CV, and then you have like C equals Q over V, right? So I'm going to do V equals Q over C to find the amount of voltage in that 3 microfarad. So I'm going to do 2.4, so Q is 2.4 E negative 5, divide that by 3 E negative 6. And so this is going to be 8 volts going down that, okay? And then I know what's going down the microfarads is that if this chews up 8 volts, well, there's 4 volts going down these 2 legs, right? Because we have a total of 12 volts, okay? The charge we know is 2.4 times 10 to the negative 5th total, okay? And now I just use my Q equals CV to find the charge in the 5 microfarad and the 1 microfarad. So I go 5 exponent negative 6 times 4. So this is going to be 2 times 10 to the negative 4th coulombs. And then I got 1 exponent negative 6 times 4. This is going to be 4 times 10 to the negative. This would be a 6, not a 4. Okay, so there they are. There's the charge and the voltage and the capacitance, right, down each of the capacitors in the figure. And so we know that, so it's just like the junction rule, right? If there's so much charge coming out, it has to be the same amount of charge, right? So the 2 times 10 to the negative 6 and the 4 times 10 to the negative 6, right? Sorry, this is a 5, not a 6. Right? Those two have to add together to give us the total. Right? And they do. All right, let's look at ranking tasks, because remember, the AP test is, fairly recent, has liked to use ranking tasks. So we're going to rank these in smallest from largest to smallest, the equivalent capacitance, right? And so we're looking at, adding and doing our 1 over bit. So this is going to be 5 micro, or we have to convert because the equation really only uses, the purpose is to really only use that, the conversion to use farads. And so this is going to be 5 times 10 to the negative 6 farads. Here we're going to simply add these two. So this is going to be 6 times 10 to the negative 6 farads. For C, we're going to do our 1 over. So it's going to be like 1 over 3 times 10 to the negative 6 plus 1 over 3 times 10 to the negative 6. And that's going to equal 1 over our equivalent capacitance, which ends up being 1.5 times 10 to the negative 6 farads. Okay, because that ends up being 2 over 3 times 10 to the negative 6. You flip it, it's 1.5. Okay, now for the next one we're going to do, I have to do a little bit, right? So we know we're going to have 1 over 4 times 10 to the negative 6 plus 1 over 4 times 10 to the negative 6 to eliminate these two in series. And so that ends up, being 2 times 10 to the negative 6 farads. And now we add it to 3 times 10 to the negative 6 farads, and that gives us a total of 5 times 10 to the negative 6 farads. And so what you can see is that A and D are tied, right? They both have 5 times 10 to the negative 6. But how do the rest play? So B is our largest, and we're going to go again from largest to smallest. So B is our greatest, then we have A and D are tied, and then we finally have C bringing up the rear. So it goes B, so B, A, so 1, 2, 2, 3, right? Again, AP is bringing in these ranking tasks, and they really like in doing them. Okay, so in the next video, we're going to take those two circuits we talked about in this whole unit and combine them into a single circuit and do kind of analysis using that.